Hi, my name is Kip Neiman, and this is part 7 of my series on a fluent example using user-defined functions. In this section of my video, I'm going to go line by line and explain each piece of the define, execute, at end code. And so, unfortunately, I can't show the entire code as I talk about each piece, so you might have to go back and refer to the full code in order to understand what's going on. But I'll go through each line here. So the first line is the include UDF.h, which again is to include a header file called UDF.h. The define execute at end, UDF starts with this command here. And basically the idea behind define execute at end is to perform whatever actions you include in this UDF at the end of each iteration for a steady state simulation or time step for a transient simulation. The only argument to this is just the name of the UDF that you pick. The next lines involve defining two integers, one I'm calling face ID and one I'm calling fluid ID. And basically the face ID represents, these are numbers that I get from Fluent. And I need to actually put them in my UDF. So this is a way of telling the UDF which face I want to consider. And so the reason why I included face ID equals 5 is because the outlet face ID in my original simulation said ID equals 5 as shown in this figure here. And basically the point of this define execute at end is to look at the conditions of the outlet face. And so when I originally did the simulation, it was ID equals 5. But it may not always be ID equals 5. And in the case of the simulation I made while I was making this video, Fluent assigned it as ID equals 6. So in order to, you want to make sure that the numbers are correct because they might change depending on the order, whatever Fluent decides to assign the different faces when it opens Fluent. So if you wanted to use this with with my newer simulation, you'd have to use 6, but I'll leave it as 5. For now. And so both of these lines, I should say the fluid ID equals 1, this is to tell what the interior boundary condition is from Fluent. And so 1 basically means the fluid boundary condition. If you want to, there's also comments shown here. So if you want to include comments in the code, you could use this / star at the start and the * / at the end and put the comment in between. The next 3 commands are file *fp, domain *t, and threads *t. And basically here I'm defining pointer variables, and these are variables to represent a location in memory. So the first is required for printing out the file. So this is the file *fp is because I'm going to be actually printing out a file with this UDF. The second, domain *d, is for the fluid. And the third is for the thread, so like a face thread as the outlet. So the question you might ask is, like, why did I create these pointers? And basically because the Fluent customization manual told me I needed to do this to accomplish my goals in my UDF. And so if you look through the examples in the Fluent manual, you'll see where they include these kind of commands, and you can just kind of mimic them. So the next line is this is again real time equals current _ time. This is basically just pulling the current simulation time and storing it as a variable called time. The next line, D equals get domain fluid ID. We defined fluid ID before in the previous slide as 1. So what this does is this retrieves a domain pointer for fluid ID, which is ID number 1. And stores it as a variable D. And so in general, single phase flow, Fluent will select the 1 as the ID, but for multi-phase flow, you'll have to look and set it. So specifically, if you go to Setup, Models, Multi-Phase, and go to Phases, there's a Phases tab in the window that opens, and all the ID numbers are listed there. So basically to show you where it's at, Setup, Model. So if I go to Setup, Models, multi-phase. So right now, multi-phase is off. But if it was on, this phases tab would be visible, and you can click on that, and in there will list all of your phases and the corresponding IDs. Next is this lookup thread macro. So it's similar to the get domain macro, except that this one gets the thread. It is the thread associated with an integer zone ID number, which is face ID in this case, and the domain, which is D in this case. So D came from this previous get domain command, and face ID we defined on the previous slide is equal to 5 because 5 corresponded to the outlet surface in my simulation. Next, I'm going to this face underscore TF declares a variable called F to represent a face, and we do this so we can iterate through the faces later. And is similar to what I did in the previous UDF. I'm going to define A, and again use this nd underscore nd thing. And so the point of this is to declare a local variable, which is an array for representing the area normal vector of a face. And so I'm going to be, as I'm iterating, I'm going to be changing the values of this A vector depending on which face it's looking at in the loop. And so again, this nd is used to set the length of A to be whatever is appropriate for your simulation. Following this, there's a series of variables I defined. So these all have meanings that I give them, so I'm going to explain what I mean by each one. Total area represents the sum of all the areas of all faces being considered on the thread being considered. Face area is the area of a single face, which will come up as we're iterating and summing to get the total area. Some face temps represents the sum of the temperatures of all faces, where in face temp represents the temperature of a single face. And so when I'm iterating through, I'm going to add each individual face temp to the sum to get the total. And then sum temp times area, so this is basically each face temp times each face area, so you end up with this summation of TI AI, where TI is the temperature of face I and AI is the area of face I. And then if you take this expression here and divide it by the sum of the of AIs, you get the area weighted temperature. This is just a formula for the area weighted temperature. And so the following command is this begin F loop, which is a loop that loops through all faces in the thread T1. Actually, here it's just T. Then inside of the begin F loop, there's this if statement that says if principal face P. So this is important here because this principal face is this is needed to avoid counting the faces more than once. So the idea is this principal face P is going to evaluate to 1 when a face is a principal face, otherwise it's 0. So if it's 1, it'll do whatever's inside of this statement. If not, it won't, and that basically avoids counting non-principal faces. And this avoids the double counting issue. Next, there's this macro to pull the temperature of face F belonging to thread T. It says F underscore T. This line here, sum face temps equals sum face temps plus face temp, is where I'm summing all of the individual face temps to get the total surface temperature. F area, AFT, is basically a fluent macro that finds the face area vector, which is also called the face area normal of a given face F in a face thread T, and it stores the result as A. And so this is actually similar to a command in the previous UDF, which I'll go to that really quickly. This is very similar to the F centroid, except now we're looking, instead of finding the coordinates of the centroid, we're finding the area normal. And so, next after this F area is using a macro called nv underscore mag, where I take the A, which is a vector of 3 values representing the normal of the face, and it basically calculates this macro nv underscore mag calculates the magnitude of the vector, and basically that is the same as the face area, the area of sorry. Since the vector is the face area vector, this macro gives us the area of a face. So in general, if you have, anyway, and then, sorry, total area equals total area plus face area. So this is where I'm taking each individual face and summing the total areas on the outlet. And then this here is calculating the summation term, the numerator of the area weighted temperature. So one thing I will say is this line here where it says sum face temps equals sum face temp, where it's summing all the face temperatures together. Sorry. The sum face temperatures equals sum face temps plus face temp. This line here where it's calculating the face temperatures of all of the faces at the outlet, this value is not really meaningful. I'm just putting it here because I don't know. There's not really a reason why I have this here. Because you don't actually need this value in order to calculate the area weighted average. The next command you will see is it says if exclamation point RP underscore host. And these are there's a beginning if statement and an end if statement. Because it has this pound sign or hashtag, it's called a compiler directive. And basically, the commands within this if statement are only performed on compute nodes and not the host node. So what the explanation point indicates is it's RP host refers to the host node, and if I put an exclamation point, it negates it. So that basically means any node besides the host node. And the reason why this is important is because the code, it prevents the division by zero. So this comes from the formula of the area weighted average, which involves dividing by the total area. So where you sum all of the individual face areas. And since the host node does not contain the mesh information, this value will be zero. So you end up with like a nonsense value. It'll divide by zero and then mess up your results. And so next I have these commands here are important. What they're doing for all of them, they're all applying this macro called PRF underscore GR sum 1. And basically this is one kind of global reduction macro is what they're called. And what it does is it collects data from all of the compute nodes and reduces the data to a single value or an array of values. So in the case of PFR GR sum 1, this specifically sums all of the values among all the compute nodes. So what I mean by that is that each compute node finds total area, which is the sum of the areas of the faces for a given thread, for its partition, and not the entire geometry. So, yeah, I'm only looking at the sum of the areas of the faces for the outlet. To find the total area, we must sum the values from all partitions because some of those faces will be in one partition, and some will be in another partition, and some will be in another partition, and so each partition will only have part of the total sum. And so we need to take all those values and sum them together. And that's essentially what the purpose of this PFRGRSM sum, it should be sum. I'm missing a U. And so what it basically does is it takes the whatever individual value of, for example, sum face temps on each node, sums all of the values on all of them together, and it replaces the variable with the actual sum. So now all the compute nodes will contain the sums of these values. And so finally, the last step is just to divide that summation, sum temperature times area, and divide by the total area to calculate the area weighted temperature. The last part of this code is for printing out the results to a text file. So I'm going to start with this if statement. The point of this statement is to ensure that the results are only printed once. And the reason why this does this is because it only lets the printing statements work if we're considering node 0. So if you remember, node 0 is a node that communicates with all of the other compute nodes. And so it has the information that we need, and we just pull the information from there instead of pulling the information from every node. So if you don't include this statement, it'll repeat the values many times because it's gonna, for each node, it'll give you the value that you're printing out. And so specifically, this I am node 0 P evaluates to 1 for compute node 0 and equals 0 for the other compute nodes. And so essentially, this will make it so the results are only printed once. And the kind of operation this is called is a predicate. And in general, predicates are macros used to test conditions on UDFs. And so you can look up and see other predicates in the manual. This part here is printing the results to the console. So the console is on the right here. It says console. So you can print results to a file. I also here have printed results of this console so that between each time step it'll show information as your simulation is running. And so for this, I'm using printf commands. And so these printf commands are similar to the fprintf commands in MATLAB, but note that there's only a single f and not fprintf. So if you use MATLAB, what you can do is you include in quotes what you want to print, and then whenever you want to include a variable, you put like %f or %, in this case I put %1.5f, and then you include all the variables after the quote. And so what I'm doing here is just printing all these values to the console. And you can, if you need more about the syntax, you can actually look at the MATLAB documentation, because it's really the same syntax, except that these are printf commands, because fprintf is used for printing to the text file, which I'll talk about in a second. Following these commands, there's this flush stout command, which is a standard C command. And this is specifically used to clear the output buffer, and this ensures that any buffer data to be written to the standard output is actually written. And this can be useful when you want to ensure that data is displayed immediately rather than being held in the buffer. And so it's good to put this after printf commands, because sometimes issues will happen if you don't. Next, I have this fp equals fp open, and then the name of a text file, an A, and then this is a statement that has an open and then a close. And so basically inside of these open and close, you use fprintf commands in order to print to the text file. This fp is actually from the beginning of the code where we defined a pointer called fp. So we want to make sure we reference this fp here. Data define executed in.text. This is the name of whatever text file you want to write to. This A indicates append, because if you use W, it'll write, but the issue is that every iteration it'll rewrite over the previous. So if you put A, it'll append to the previous, so that it doesn't rewrite information. The file path is here. This is actually the same place where you put the UDFs when you're running the simulation. The last thing here is just the fprintf commands, which again, this is basically identical to the syntax in MATLAB. And note the two Fs here for printing to a text file versus the single F here for printing to the console. And so in order to connect the UDFs to a simulation, we do something similar where we're going to click on user defined and go to compiled. And then I'll show you how that's done. So I'm going to go to user defined functions compiled. In this case, first I need to take my UDF, which is executed in here. I'm going to copy this and place it in the same folder as before. So under DP0, FFF, Fluent. So here I can place this executed in the same spot where I place wall profile. And then when I go to under compiled UDFs add, I should see both. So I'm going to click on each one once and then click OK, and you can see they're both added to this. And then I click build. And when I click OK, it's going to do the same thing before where it prints out some things, and you want to check and make sure there's no errors here. And if there's no errors, it means it means it's successful. If you see errors, there's probably issues with your code that you should debug. And then click load. And so like I talked about previously, if I want to hook the UDF to the wall, I wanted to add a temperature profile along the wall in the previous UDF. I went to this wall here and I double clicked and went to thermal. And again, I went to temperature and I selected the UDF from this drop down list. The way that the define executed ins work is a little different. What you actually do is you go up to the top where it says function hooks and click this. And then you need to click on this edit button next to execute at end, and you should see the name of your UDF here, and you just click add and then OK. And OK again. And now you should be ready to run your simulation with that the define executed end. And so at this point, you can run the simulation the same as before. So here's some slides explaining the process. So then basically we would now have added both UDFs. I won't bother running it, but you can run it and you'll see printouts in the console, and there'll be a text file that'll appear at this folder, the same place where the UDFs are added. Okay, thanks.